Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we're going to learn about the Bellman-Ford algorithm. Now this is again an algorithm which will help you to find the shortest path. Yes, I might be thinking, but Striver, we already know an algorithm like Dijkstra, which helps us to find the shortest path. How is this different? It is the exact similar algorithm which will help you to find the shortest path from a source to all the other nodes. Yes, to all the other nodes. But the only difference is, if you remember the video of the Dijkstra algorithm fails when the graph has negative edges. Please remember, if the graph has negative edges, the Dijkstra algorithm will fail. And there was another point, if the graph has negative cycle, the Dijkstra algorithm goes for a TLE, like it will keep on running, it will keep on running, keep on minimizing the distance, it keeps on running forever. So Dijkstra does not helps you to detect negative cycle. So Bellman Ford is an algorithm that helps you to detect, remember this, that helps you to detect negative cycles as well. That's the specialty about Bellman Ford, and it is applicable, and it is applicable only in DG. What is DG? Directed graphs. Now you might be thinking, what if it's an undirected graph? Then how do you apply Bellman Ford algorithm to it? Very simple. Remember, this is how a directed edge looks like. So the edge weight will be 5. So there is an edge from 1 to 2 and the edge weight will cost you 5. But imagine if I give you an undirected graph and I say 1 to 2 and the edge weight is 5. So in order to implement Bellman Ford, you need to convert this into something like 1. There is a directed edge from 1 to 2 which will cost you 5. And there is a directed edge from 2 to 1 which will cost you 5. So you just need to represent the undirected graph in form of a directed graph in order to implement the Bellman Ford algorithm. The Bellman Ford algorithm will only work if you are given a directed graph. Remember this. So if you are given an undirected graph, just change it to a directed graph by having two side edges with the same edge weights. That is how you can always implement Bellman Ford for any of the questions. The only difference from Dijkstra is it helps you to detect negative cycles. What do you mean by negative cycles? Imagine I draw you a graph which goes from 1 to 2, 2 to 3, and 3 to 1. And the edge weight is -2, -1, and something like 2. So if I ask you the path weight, what will be the path weight? The path weight will be very simple. It will be -2, -1, +2. So -2 plus 2 will go, and the path weight is basically -1. So if you apply Dijkstra, it will keep on rotating, keep on encircling in the path because the path reduces at every stage. So thereby Dijkstra will fall under the TLE loop for such an example. But when you talk about Bellman Ford is an algorithm specifically designed such that it will tell you that, hey, listen, this particular graph has a negative cycle. This is what you call as a negative cycle if a path weight is lesser than 0. If a graph has any path weight which is lesser than 0, then I can say that the graph has a negative cycle. Now let's try to implement the Bellman Ford algorithm. So I will be taking this particular DG, which is the directed graph, in order to implement the Bellman Ford algorithm. And we know that it is a single source shortest path algorithm. So the starting point is 0, and these are the edges given to you. So the edges will be given like U and V, which means there is an edge from 3 to 2 with an edge weight of 6. There is an edge from 5 to 3 with an edge weight of 1, which is very obvious. If you see, this is this particular edge. And if you look at 3 to 2, this is nothing but this particular edge. So all the edges are given to you. Now something very, very important to note down. Edges can be given in any particular order. Yes, edges can be in any order. Like, it's not necessary that you have to follow any particular order. If you carefully see, you can have 3 to 6 at the top, you can have it here, you can have it here, you can have it at the bottom. The edges can be jumbled, it can follow any order. What matters is you have to have all the edges of the directed graph. The order can be anything. Very, very important. Edges can be in any order. Now, what does Bellman Ford state? The Bellman Ford will state you have to relax all the edges. Remember this. Relax all. Very, very important. Relax all the edges n minus 1 times sequentially. Very, very important point. Now, what do you mean by relax? Yn minus 1, everything you will understand if you watch the video till the end. So, what they're saying is relax all the edges n minus 1 times sequentially. Now, what is the definition of relax? Let me write that as well. So, the definition of relax states if you have a distance array and if the distance taken to reach u plus the edge weight that you require. For an example, you're standing at 5 and you want to go to 3. The edge weight is 1. So this is the edge weight that I'm talking about. So if the distance of u plus wt is lesser than, very, very important, is lesser than the distance of v, which means as of now, you're at 5, now you're trying to go to 3 with a 1. So whatever distance you took to reach this u, which is 5, so basically distance of 5 plus this 1, if that is smaller than this, whatever you took to reach 3, then you got a better guy similar to Dijkstra. So what you'll do is you will simply go ahead and say, okay, I got a better guy. So I'll be like distance v is equal to the new distance, which is distance u plus w. This is what I call as relaxation of edges. This will be done for n minus 1 times. What do you mean by n minus 1 times? If you go over here and look at the n over here is 6 because there are 0, 1, 2, 3, 4, 5 like zero based indexing edge nodes. So thereby n is 6. So you have to relax it for 5 times. 5 iteration of relaxations has to be done. Now, how to do it? Let's understand that. But before that, since you are calculating shortest path, what do you require? You require a distance array with everything initialized to infinity. So let's do that. So initially, when you initialize the distance array, the source will be marked as 0 and everything else will be marked as infinity because you haven't reached anywhere. So as of now, you know you're starting from here and that is always going to be taking a distance of 0, but you haven't reached something like 1, 2, 3, 4, 5. So what you do is you just initialize them with infinity. Now, how many iterations or how many relaxations you need to do? N minus 1. What is n? 6. So remember, you have to do 5 relaxation is what you need to do. Now, on the first relaxation, let me explain you. If I say first relaxation, what you need to do is, now on the first iteration, what you'll do is, you'll go across the first edge, second edge, third edge, and so on till the last edge. You have to go across all the edges. And that is when you say first iteration is done. On the second iteration, you have to go across again. Third iteration again. Fourth iteration again. Fifth iteration again. You have to keep on going, keep on going, keep on going for 5 times. Okay. So when I say first iteration, what does that mean? That's very, very simple. You have to perform this thing on every edge one by one. That is what you call as one complete iteration. Okay. So the first iteration, what will happen? The relaxation of this edge will happen, then this. So let's do the relaxation of the first edge. Very simple. I know I'm starting like distance of 3. I will take 6 in order to reach the distance of 2 because from 3 to 2 is where I need to go and I'll take a 6. So what is 3? If I look at 3, the value of 3 is nothing but infinity. So if I haven't reached 3, is there a point in going ahead with 3? I haven't reached 3. So there's no point, right? So the relaxation of this edge is done. Next, you go to this edge. It's like from 5 to 3. Cool. Let's again do the relaxation. From 5, you take 1 and you reach 3, right? So can I say 5 is still infinity? So you haven't reached 5. So if you haven't reached 5, there's no point. Next is this one, which is 0 to 1. So you're like, you can start from 0, you will take 5 and you will reach 1. So when you say distance of 0, it says, yes, I have reached myself. It's a 0 distance because I'm the source. Plus I'll take another 5 and I'll reach the 1, which was previously reached with infinity means not reached. So I've got 5. So I can go and update this to 5. So on relaxation, I update one of the nodes to 5. Perfect. Next is this guy which has to be relaxed, which is distance of 1 minus 3 lesser than distance of 5. Very, very important. Distance of 1 minus 3 lesser than distance of 5. So if you carefully see, we have a 1 here, right? Do you see? We have a 1 here. So how much has 1 taken as of now? 1 has taken a 5. So it's like 5 minus 3 lesser than distance of 5, which is infinity. So 2 lesser than infinity. So I can reach 5 in distance of 2. So go and update this with a distance of 2, and I can say the relaxation of this particular edge has been done. Next is this guy. So let's quickly relax this as well. This is nothing but you can write distance of 1 minus 2 lesser than distance of 2. Again, what is distance of 1? If you carefully see, it's nothing but 5. 5 minus 2 is 3, which is lesser than infinity. So you get 3. So go and update this to 3. Perfect. Done. Next, you will go across and do this particular iteration. So this is nothing but 3. So you can again write distance of 3 minus 2 again lesser than distance of 4. That's what you can easily write. And can I say, if you, why is this coming up again and again? Wait. So what I can say is, what is distance of 3? Can I say this, that distance of 3 is still not infinity, so this will not be done. Next is the last edge, which has to be relaxed. So let's quickly relax the last edge, which is nothing but distance of 2 plus 3 lesser than distance of 4. What is distance of 2? Let's see. Is 3. So 3 plus 3 is 6. What is 4? Infinity. So can I say this will be updated to 6? So what I can say is the first iteration has been completed. And on the first iteration, we have got the updated distance values. Okay, now you have to again do it, which is the second iteration. And the second iteration, what you'll do, you'll again start, yes, you'll again start from the first. Now, what is distance of 3? Infinity, not reached. What is distance of 5? This time you'll find 5 has been reached with a distance of 2. Why did you find? Because in the first iteration, when you went, 5 was updated somewhere here. And now again, when you come back and restart, that 5 value which you updated here will be in use here. So what is the 5's value? 2 plus 1, which is 3, lesser than infinity. So this will go as 3. So go across and update 3 as 3. Perfect. Next one, this one. What's the value of 0? 0. So 0 plus 5 lesser than 1. That's still 5. Not to be done. What is 1? 5. 5 minus 3 is still 2, which is lesser than, not lesser, so not to be done. Again, let's check out this. What is 1? 5 minus 2, which is 3, which is still not lesser. What is distance of 3 this time? This time distance of 3 has been computed. What is distance of 3 this time? 3 minus 2, which is 1, says 4. Is it lesser than 4? Yes, because 4 is 6. So if you see 4 is 6. So what I'll do is I'll say distance of 3 was 3 minus 2 is 1, which is better than the current distance. So I'll go and update this to 1. Very simple, because I started with 3 and I'll take a minus 2 distance in order to reach this guy. Again, the last guy is this, which is nothing but 3 plus 3 again 6, which is not better than this. So I can say the second iteration is also done. Similarly, you will do the third, fourth, and fifth. Basically, again ramp, again ramp, again ramp. And once you have done this, this particular distance array will be storing all your shortest distance. Yes, it will be storing all your shortest distance. And if you carefully look at this, it does not have a negative cycle. It does have negative edges, which is allowed, but it does not have a negative cycle. So ultimately, after all the 5 iterations or n minus 1 iterations, your distance array will be giving you the shortest path from the source 0 to all other nodes. Remember this, which will be stored in this distance array. Now, a couple of questions. Why n minus 1 iterations? That's the first question. And the second question will be definitely how to detect negative cycles. What if the graph has negative cycles? How will I know about that? So, because the entire algorithm is pretty much similar to Dijkstra because this portion is similar to Dijkstra. The only thing that we are doing is we are just doing n minus 1 iteration. So obviously, I want to know n minus 1 iteration because the thought process is kind of clear. But why n minus 1 is my question. The thought process must be clear. Why? Because we just move ahead and this guy was updated. This updated 1, then with the help of the 1, I got updated 5. Then again when I came back, with the help of 5, I updated 3. Then again when I went with the help of 3, I updated 4. And it went on moving. So eventually everyone was getting updated on all the iterations. So ultimately, but how did I know that on n minus 1 iterations, I will get my answer? That's my question. Because what if I would have done 2 iterations? What if I would have done 3 iterations? The question still lies, why exactly n minus 1 iteration has been done? So let's understand that as of now. So in order to understand the intuition, or why n minus 1, because that is the critical question here, because we have understood the thought process. We knew 1 helped me to compute, because we knew 0 was the source which helped me to compute 1. 1 helped me to compute 5 and 2. And similarly, 2 helped me to compute 4. Right? And when I came back, since I had computed 5, this 5 helped me to compute 3. And eventually this 3 helped me to compute 4. And so on, it will just go on this loop. Thought process is clear. But why n minus 1 is still the question. Let's understand this with this particular directed graph. So in this directed graph, if you remember, while explaining, I did tell you edges can be in any order. Edges can be in any particular order is what I always stated, right? So imagine I give you the edges in this particular order. So how many nodes are there? The number of nodes are 5. So how many iterations will we have? We will have 1, 2, 3, and 4 iterations because edges are 5. So I have to do n minus 1, which is 4 iterations. Correct? So now what I'll do is I will start off with the distance array. So let's quickly have the distance array. So again, to ease out understanding, I have kept 0 as the source and made it a distance of 0. Okay. Now let's do the iterations. So the first iteration states, this is the first edge. So it states, okay, distance of 3 plus 1, are you lesser than distance of 4? And it's like, distance of 3 is still infinity. No. Goes to the next one and says, distance of 2 plus 1, are you lesser than 3? And I see distance of 2 is still infinity. No. Next one will be distance of 1 plus 1 is lesser than distance of 2. I'm like, 1 is still infinity. No. Next, I'll be like, distance of 0 plus 1 is lesser than distance of 1. I'll be like, wait, 0 is 0 plus 1 is lesser than infinity. So 1 goes as 1. So go and update 1 as 1. Perfect. So in one iteration, at the end of the day, this one was updated. So first iteration done. Okay. Now let's talk about the next iteration. Next iteration, what is 3? Infinity. Next iteration, what is 2? Infinity. Next iteration, what is 1? 1. So 1 plus 1, 2. So this will be updated to 2. So let's update it to 2. Next, 0 plus 1, not to be done. So second iteration done. So did you see what happened? In the first iteration, the 0 got the value of 1. In the next iteration, since you had the value of 1, that one helped you to get 2. So the third iteration, what will happen? Come on, what will happen? Think. Yes, you are correct. Yes, you are correct. In the third iteration, we don't have 3. But the second iteration gave me 2. When I go to relax the next edge, this 2, who has a value of 2 plus 1, will go ahead and update 3. So 3 will be updated to 3. Perfect. Amazing. So I see this is done. Next, no more updates, no more relaxation. Third iteration done. Third iteration. Now, What happened in the first? 0 updated 1. What happened in the second? 1 updated 2. What happened in the third? 2 updated 3. So what will happen in the fourth? What will happen in the fourth? Yes, yes, yes. The 3 that you got will help you to update 4. So what did you get? 3. It says 3 plus 1, 4. So this will go as 4. So ultimately on 4 iterations, can I say ultimately on 4 iterations, the distance array is ready. And this is your shortest path. Yes. This is your shortest path. Can I say this? I can. So thereby, did you understand why n minus 1? Because at the worst case, you can have the guy at the bottom who will give you this. Then this will give you this. And then this will give you this. And then this will give you this. That is why n minus 1. That is why n minus 1. Yes. I hope that's clear. I find a lot of content over YouTube, but no one will say you why n minus 1. They'll be like, n minus 1, let's do it, let's do it. We got the answer, code it, and that's done. This is very important. The thought process, the intuition, and the clarity about an algorithm is very, very, very important. Now, the question is how to detect negative cycle. Again, thought process. Since I knew negative cycle means if I keep on, because this will give you minus 1. Again, if I rotate, it will give you another minus 1. If I rotate, another minus 1. On every rotation, you are decreasing the path value by minus 1. So what will happen if there is a negative cycle? So what will happen is if there was 5 iterations, if you do the 6th iteration, the values will still reduce. The values will still reduce on nth iteration. The relaxation will be done. And if the distance array gets updated, because we have proved that at max we will be requiring n minus 1 iterations, we have proved. But even after that, if I require on the nth iteration, if I do a relaxation, and even if I see distance gets reduced, I will be right. Negative cycle exists because I know at n minus 1 iterations, I should have gotten my answer. But if at the nth iteration, if there is still a reduction, it means we are running on the loop. We're running on the loop. That's why the distances are reducing. So both the questions answered. So it's now time to code it up. So I hope you've understood the entire algorithm. Now it's time to code it up. So as usual, I'll be coding the C++ on the right, and you can figure out the exact similar Java solution on the left. So given a weighted, directed, and a connected graph of V vertices and E edges, find the shortest distance of all the vertex from the source. So they'll be giving you a source. If the graph contains a negative cycle, then return an array consisting of only minus 1. And I think they've also stated if you cannot reach anyone, you have to assign it with 1E8. So what I will do is I have all the edges. So I need the distance array. So let's quickly have the distance array of V, 1E8 because I'm assuming I cannot reach them. So that's what I'll give. And now what I'll do is I will do the iteration or the relaxation for V minus 1 time, because that is what I have clearly stated, that I'm going to do the relaxation for V minus 1 times on all the edges. Remember this, I'm going to do it on all the edges. So this is 0, this will be V, and the WT will be IT of 2. Very, very simple. Okay, now what's the next thing that I'll do? I'll have to do the relaxation of edges. So it's something like distance. Remember, you have to give the distance of source as 0, otherwise you'll have an issue. So remember, distance of 0 should be reachable, which means it should not be infinity. It should not be 1E8. And distance of U plus WT lesser than distance of V, if that's the case. If it's reachable, and if it's the case, I say, okay, cool. Distance of U plus WT is what I'll do. So this is how the Bellman Ford will make sure the distance has the answer. Ideally, you should have returned this, but in the question they have stated what code would have finished here, but they have stated if it contains a negative cycle, then return an array consisting of only 1. So you have to do one more relaxation. This is the last, or you can say the nth relaxation to check negative cycle is what you have to do. Return an array consisting of only one. Remember this. So basically, do one more relaxation, which is nothing but this. So you can say int u equal to it of 0. You can say int v equal to it of 1. You can say again the same thing, it of 2. And you can go ahead and write the same if condition. So probably I'll copy paste. I don't want to write it again. And if that's the case, you have to return an array which consists of only one. That's it. And if that's not the case, because you cannot reduce at the nth iteration, you should have computed all the shortest path in n minus one iterations at the worst case. So what I'll do is I'll go and compile this and see if it is running fine. It is. Now let's quickly submit this. Looks like all the test cases do pass. So guys, that is it about the Bellman Ford algorithm. What about the time complexity? V into E. Very simple. V cross E is the time complexity. The space is you're using an external V space and the edges is stored. So pretty simple. Now this is kind of a quadratic time, whereas the Dijkstra was E log V. So this is taking a bit more time than Dijkstra, but it is very useful if your graph does have negative edge weights, because Dijkstra does not work. So make sure if your graph has negative edge weights, or if the graph has negative cycles, that's when you should implement the Bellman Ford algorithm. Do you get follow-up problems on this? Usually not. In interviews, they will generally ask you to tell about the Bellman Ford, or maybe they will ask you about Dijkstra. And at the end of the day, they will ask, what if the graph has negative edges or the cycles? What will you do? So it might be a follow-up question on Dijkstra. So very, very important. But I do not think the questions, like you will find questions straightly related to Bellman Ford, because most of the questions are solved using Dijkstra's algorithm in shortest path. So guys, I hope you have understood everything. So just in case you did, please make sure you like this video. And I was checking our statistics. Half of our audience does not subscribe to us. They just watch our playlist and go. So if you are watching this playlist, please make sure you subscribe to us, because that does matter to me a lot. So please make sure you hit that subscribe button. And yeah, if you haven't checked out our DP series and the SD sheet, the links will be in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye bye. Take care.
Whenever your heart is broken.